All right, future doctors, welcome. Today, we're diving into a chapter that, let's be honest, can feel a little heavy. Mechanical properties of solids. But we're not just going to read from a textbook. Oh no. We are building a strategic playbook. We're going to look at actual past year questions and spot the patterns NEET loves to use so you can solve these problems faster and, with a whole lot more confidence.
Look, we have all been there. You open the book and it's just a sea of symbols, variables, and constants. It's totally overwhelming. But what if I told you that most of the NEET questions from this chapter fall into just a few super predictable patterns? Seriously, if you can master the patterns, you will master the chapter. So let's jump right in.
Okay, first things first, the absolute basics. Everything, and I mean everything in this chapter, is built on two key ideas: stress and strain. Just think about it like this. Stress is the force a material feels on the inside. Strain is how much it changes shape because of that force. It's that simple. Force goes in, deformation comes out. Let's see how NEET uses these ideas.
Okay, let's get to our first and honestly one of the most common patterns, the ratio question. Now NEET loves these, and here's why. They're not just testing if you can plug numbers into a calculator. They want to see if you really get the relationship between the variables. Spotting this pattern is your first big shortcut.
So here's a classic example. This is the kind of question you will see over and over again. You've got two different wires, different lengths, different areas. But the biggest clues are right there in the problem. They stretch by the same amount, under the same load. The goal? Find the ratio of their Young's modulus.
Now, you might look at this big formula for Young's modulus, Y, and your first thought is probably, okay, I've got to calculate everything: force, length, area, change in length. But wait a second, that's the slow way to do it. The real secret to any ratio problem is figuring out what you can completely ignore.
Here is the speed strategy. First, we isolate Y. That's what we're looking for. Now, what did the problem say was the same for both wires? The load, which is force F, and the stretch, which is delta L. Since they're the same for both wires in our ratio, we can just get rid of them. They cancel out. This one simple step lets us forget about the constants and focus only on the stuff that's actually different, the original length and the area. And when you do that, when you focus only on the lengths and areas from the problem, boom, you get your answer. The ratio of the Young's modulus of steel to copper is 1.79. No messy calculations, just some smart simplifying. And that is pattern 1 locked in.
All right, let's level up and move on to our second pattern. See, NEET isn't always going to give you the numbers neatly in a paragraph. They absolutely love to test your understanding visually, and their favorite way to do that is with stress-strain graphs.
So take a look at these two graphs. We've got material A and material B, and they're drawn to the same scale. The question is simple. Which one of these is stronger? And which one is a greater Young's modulus? Just take a second, look at the graph, and think about what those two things mean visually.
So here's the deal. Strength and Young's modulus are two completely different properties on the graph. Strength is all about the maximum stress a material can take before it snaps. That's the highest point it reaches on the vertical axis. Young's modulus, though, that's about stiffness. And stiffness is just the slope of that first straight part of the line. So in this case, material A goes higher and has a steeper slope, meaning it's both stronger and has a greater Young's modulus.
Okay, let's switch gears from just comparing to actually calculating. Here is a typical graph you might get on your actual NEET paper. The question here would be something like, calculate the Young's modulus of this material. And again, the answer is just hiding there in plain sight on the graph itself.
Just remember this: Young's modulus is the slope. That's it. It's the slope of that initial straight line part. And how do you calculate a slope? It's just rise over run. In our case, that's stress divided by strain. All you have to do is pick a nice, easy point on that straight line, like here, where stress is 150 times 10 to the 6 and strain is 0.002. Divide one by the other, and there's your answer. It really is that easy.
Let's move on to pattern number 3, the conceptual check. Ah yes, these are the ones that are often true or false, or just direct questions that are designed to catch you on common misunderstandings. They test if you really get the physics behind all the math.
So here is a classic trap. Is the Young's modulus of rubber greater than that of steel? Now your gut might say yes, right? Because rubber is so stretchy. But you're thinking about it backwards. Young's modulus is a measure of resistance to being stretched. Steel resists being deformed way, way more than rubber. You need a massive amount of stress to get a tiny little bit of strain in steel. And for that reason, steel has a much, much higher Young's modulus.
Okay, let's try another one. This is a good one. Picture a coiled spring in your mind. When you stretch it, what are you actually doing to the wire? Are you making the wire itself longer, or are you just changing the shape of the coil? This question gets right to the heart of why we have different moduli.
So the answer is you're changing its shape. When you pull on that spring, the wire itself doesn't really get any longer. What's actually happening is it's twisting. And any change in shape that comes from a twisting or a sliding force, well, that's governed by the shear modulus, not the Young's modulus. It's a subtle difference, but it's exactly the kind of thing NEET loves to test you on.
And now, it's time to put it all together. Let's look at our final pattern, the multi-step challenge problem. This is where NEET takes a few different concepts and mashes them into one question, to really see if you can solve things systematically.
Okay, check out this setup. We've got a steel wire up top and a brass wire hanging from it, and together they're holding two different masses. The goal here is to figure out the elongation, the stretch, in each wire individually. To solve this, you have to be really systematic and really careful.
The key to not getting tangled up here is to just break it down into simple steps. First, let's think about the forces. The tension in the bottom brass wire? That's easy. It's just holding up the bottom mass. But, and listen up, because this is the #1 mistake students make. The top steel wire is supporting the weight of both masses added together. Once you figure out the correct tension for each wire, you just plug those numbers into the Young's modulus formula to find the stretch for each one.
And this visual just makes that difference crystal clear. The tension in that top steel wire, F1, it comes from the total mass, which is 10 kilograms. That gives us 98 newtons. But the tension in the bottom brass wire, F2, that's only supporting the 6 kilogram mass at the bottom, which is 58.8 newtons. If you get this part right, the rest of the problem is a piece of cake.
So there you have it. That's your playbook for mechanical properties of solids. For those ratio questions, just find what's constant and cancel it right away. When you see a graph, remember, the slope is the Young's modulus. For those tricky conceptual questions, you have to challenge your gut feeling. And for the big, complex problems, just break it down and check every single force, one by one.
So I'll leave you with one final question. The next time you sit down to do a practice test, which of these patterns are you going to actively look for first? Training your brain to see these underlying structures is, without a doubt, the fastest way to boost your speed and your accuracy. Now go out there and crack it.